Hello, welcome to another problem session. Today we have a problem in sound wave again. Last problem we dealt with was sound wave, and this time last time we wrote sound wave in this form with a pressure wave. This delta p. This should be delta p. So this is a pressure difference with the ambient pressure, and you can write like that. Another way of thinking about sound waves is displacement of particles from your from the equilibrium. So you can see the whole bunch. This medium is filled with particles, and particles just move from their equilibrium. So there was a particle at this place and it moved over here at time t equal to 0. Different particles, this particle was moved over here, this particle, and so it's moving. The wave is going this way. This is the wave direction. Over here, these are opposite side. This should be t here. There is a t here. Let me put a t here. X and t, these signs are opposite, so it's going in the positive x direction. This describes how much the particle has moved at t equal to 0. At some other time, when the wave has become, say, at this instant, a little bit later, then this particle had come back here. This particle has used to be here, come back here. This particle used to be here, went up here, used to be here, actually went up here. Particle movement is transverse, is along the y direction, while the wave is going in that direction. That's why it's called transverse. And the y is given the y coordinate of the particles, which used to be at y equal to on this y equal to 0. That's how it's described. And so it's particles are moving between this amplitude 2 times 10 to the power minus 3 meter and 2 times 10 to minus 3 meter down here, and described by a cosine wave. Okay, so we have lots of definition things that we should go over, and then some conceptual things down here, some calculational things down here that we have to go. And in the end, when we have gone through the definitions and some calculationals, then I'm going to connect to the pressure wave. Okay, it's going to be a little bit long lecture, but hopefully you will understand things more deeply. Okay, so amplitude of the wave, we already talked about. This is the amplitude, how much from the equilibrium it goes up or down, how far away from the equilibrium it goes. So this is the amount it goes. So this is just a 2 times 10 to the power minus 3 meter. That's the answer is for this. With the wavelength is this is equal to k, wave number. K is pi over 100, and k times lambda is 2 pi. Lambda is the wavelength. So that means lambda is 2 pi over k is put in over there, 2 pi times 100 over pi. And so this is 200, and this is a lambda, so this should be k is 1 over meter in inverse. So this is meter. That's how we get the wavelength. However, the frequency, this quantity here is wave angular frequency. So this is angular frequency in per second, so that they will cancel out. Sometimes we'll say radian per second, but dimension is per second. Frequency is so 2 pi f is omega, and omega is 30 pi. So of course you can call pi kite away, and then this cancels that, gives you 15. So this means f equals to 15 cycles per second, or 15 hertz. Speed, you can do it a couple of different ways. You can say I take this, I take ddt on that, or you can see that lambda times f equals to speed b, and you got the lambda 200 meter, and you got a 15 per second. So when I multiply this out, 300 meter per second, or 3 kilometer per second. Okay, this one is just a value of y when you set x like that. So this means y at 0, 0 is set 0, 0. So you have a 2 times 10 to the power minus 3 meter times cosine of minus pi over 6. So the cosine 30 degrees is going to be square root of 3 over 2. So this is going to be square root of 3 times 10 to the minus 3 meter. And square root of 3 is close to 1.7 times 10 to the power minus 3 meter. Okay, this looks pretty good. Okay, so how do I get maximum particle speed? This is the displacement. I just take a dy dt and see what the maximum of this will be. We want maximum of this, absolute value, maximum, that. So when I do dt, so when I do it, cosine will go into sine, which will go from plus 1 and minus 1, and 30 pi will come out. So this just will be 30 pi times that, 2 times 10 to the minus 3 meter times 30 pi per second. So multiplies like a 60 pi times 10 to the minus 3 meter per second. So that's the maximum particle speed. You can just convert that, right? So now the part that we want is intensity. Let me erase this out and get a clean space there. Okay, so for intensity, we notice that we have a medium of particles, and medium is three-dimensional, and each particle is executing up and down motion, simple harmonic motion, each particle here, and the energy is going in that way, right? So what's the intensity? Intensity is, if I take a unit area, so this area is 1, then how much energy is passing through per unit time? The wave particle is not passing, the energy is passing per unit time. So intensity definition is average area, average energy. This average over time, average in time. So I'm time average. Energy per unit time per unit area. Okay, so we notice that if the wave has velocity v, so this is the wave velocity v, then in this, all the energy that's in this box of dimension v, so this is the x, in the x direction you have a v, and this area of this area is 1. Just call it a. I'm going to just call it a script a for the area. Our area perpendicular like this. Let's call it that area perpendicular like that. So all the energy that's in this box would have passed it. Energy is consisting of motion of each one of the particles according to that, right? So and this amplitude, let's call a, and this is a perp. Okay, so this different things. These particles are and I'm gonna call this omega in just in a second. So why I'm doing this, so when I have this, each one of these particles is executing a simple harmonic motion, right? And their energy is kinetic energy plus potential energy at any time, and conserved. That means this is equal to kinetic energy maximum and potential energy minimum at that point. Or you can think of kinetic energy 0 but potential energy maximum. You can use any of these three formulas for energy. So if I look at this, what is kinetic energy maximum? Well, that's going to be half mv max square. What is this mass? This mass is all the masses that are in this box, and v max is a particle, each one of the particles motion. So v max is, we just found earlier, so they're just going to be half, let's leave it m here for now. V max is like a dy dt max square, and that just turns out to be half m. If you take a derivative, it's omega a, omega times the amplitude square. So that's the energy that's in this box, and all of that will pass through that in 1 unit time. Okay, this is the amplitude, and how much is the mass? Well, mass is so m, how much is in this box? The density times the volume of the box, and density volume is v times a perp, v times a perp, the script a perp. So if I do this, that just turns out to be half rho v a perp omega a square, but I want per unit area, so this cancels out, and so the formula for intensity is half rho v omega a square. Now we have all of these things available to us, and we can put the numbers in. This is equal to half times 2700 times v is the speed of the wave, which is the ratio of these two, which is we are already computed pi over 100. So that's a 3000, and omega is 30 pi, and amplitude is that 2 times 10 to minus 3 square. When you calculate all of this out, and I do calculate this out in here using Python IDL. So this is intensity is, if I do the decimal 1, 2, 3, 4, 5, 1.44, 1.44. So this gives me 1.44 times 10 to the power 5. What will the unit is going to be joule per second per meter square, or you might call it watt per meter square. So that's the intensity. Now, how do we, the last problem is, if I were to write this as a pressure wave, what will the pressure wave look like? Okay. So, what's the amplitude of the pressure wave will be, the last problem. And so, whether we write this wave as a pressure wave or displacement wave, intensity same, whether we think of the wave as pressure wave or displacement wave. So we're going to use this value, but apply to the formula what we'll get for the from the consideration of the pressure wave. Let me erase and just get a clean slate again. So if I want to write this as some pressure wave in terms of some quantity, some constant P0 square or something like that. So if I want to write something like that, we need to figure out what this alpha is, etc. We would be able to get this formula just from the units consideration. Okay, so this guy over here, if you remember from the displacement part, if you just look at the intensities, well, we have a half rho v, and then omega amplitude. This is amplitude square. So so you can see that there's a you have a relate this to the unit of this, right? So let's see if I can insert somehow P0, identify P0 there. So this is velocity squared. This is some kind of speed squared unit. And let's see what P0 is. So the pressure P0 has units. Units will be force over area units and area. And force is kilogram times meter over second square, and this is meter square. So this is kilogram over second square meter. Well, I see density and times, you have a velocity speed cube. So somehow I need to introduce if I do P0 square, I will get kilogram square over second to the power 4 times meter square, and I can see here it's going to go to kilogram square over meter to the power 6, so that I can get a density squared, right? And then so if I were to multiply rho over rho, this rho with this rho will be density to the power squared. And then I have meter 6, so I have a meter to the power 4 over second to the power 4. So I need to convert that into this meter. This is only so for the V and multiplied by V, then I can convert the whole thing as a so P0 will have this, P0 square will have the same unit as rho V omega A square. So if we do that, so we have, let's call this guy half P0 square over rho V. So the intensity becomes that, and so P0 is equal to 2 times intensity rho V square root, and from there I can get so this gives me 2 square root of this number 1.44 times 10 to the power 5. Density was 2700 in these units, and V was 3000 in these units. So I should get the pressure in the unit of Pascal. And let me get this answer. So when I do this out, now this 2 has to be outside, I mean not outside, this 2 is here, and when I do this out, I guess so that's the answer is 1.53 times 10 to the power 6, 1.53 times 10 to the power 6 Pascal. So this pressure wave has that much amplitude. A question that you might have in mind is, when I was writing Pxt, or delta Pxt, you have P0 and cosine, all of this same, pi over 100x minus 30 pi t. Then I wrote down plus phi, and I didn't ask you to calculate this. Well, you can actually calculate this yourself, and I'm going to leave that as an exercise, is by using a principle. So principle will be where the V is V of the particle, where dy dt is highest, where this is highest pressure. So if this is highest at, say, some x, then this take t equal to 0. Okay, so this will be highest, where this is highest, px0 dy at t equal to 0. So some x value, this is highest, px0 will be lowest, and vice versa. You can show this by using the principle, Bernoulli's principle. In fluids. Okay, so we're going to talk about fluids much later, but applying this, you can show that these are highest and lowest, means they're off by, this is off, phase off by pi radian in phase. So the phase constant here and phase constant here will be related by pi radians in that case. I'm gonna leave that as an exercise for you. Pretty interesting exercise, and I will see you in another video. Talk to you later.